Hey guys, welcome back. All right, guys. So moving along in our permutations and combinations unit. So we just finished with the first topic was all about permutations, and permutations means the same thing. Arrangements. Okay, so it's going to be arrangements over here. Now, what the topics we're talking about today is similar. Okay, we're talking about the total number of outcomes over here, but the word combinations means the same thing as groups. Okay, so combinations are groups and permutations are arrangements. Okay, so I'll show you what we mean by that. Okay, guys, just to make this a bit easier here, quick typo. Let's just say we have Andy, Billy, Charlie, and Danny. Okay, so for part A, list all the two-person arrangements. Now, just again, first of all, if I had to ask what the question was, how many arrangements? It would be 4 times 3, which is 12. Okay, now it's saying is okay, what are those 12 going to be? So here's how I can do it. I'm going to say you have Andy, Billy, and then you have Billy, Andy. So those are two different arrangements over here. You have Andy, Charlie, Charlie, Andy, Andy, Danny, Danny, Andy. You have Billy, Charlie, Charlie, Billy. You have Billy, Danny, Danny, Billy. And then you have Charlie, Danny, and Danny, Charlie. For a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 total arrangements over there. That's what we're looking for. Okay, guys, we're doing the same thing. Had there been 5 people, I would have to list out 20 of those, and it would have just been a bit too much over there. Okay, now different question. So these are arrangements. So what do you mean by arrangements? Is that AB and BA are different arrangements. Okay, so in other words, those are distinct permutations there. Okay, now for part B, it says list all of the two-person teams. Okay, so now imagine like that, you're going to say, okay, you want to make teams. So the question is, if you have a team of Andy and Billy, is that the same team as Billy and Andy? Okay, so in this case, AB and BA are the same team. Therefore, we don't count them twice. Okay, so what we have here, we have AB, AC, AD, BC, BD, and CD. So we have a total of 1, 2, 3, 4, 5, 6. Okay, so in this case, we had 12 arrangements, but now we only have 6 teams. Okay, so we're going to count the teams. Now, again, guys, just based on the language kind of matters here. But if I'm saying team, which I can see means the same thing as group. Okay, so a team or a group. Okay, well, the order doesn't matter. A, B, and BA are the same group or the same team. Okay, so we don't need to count those ones twice. There are 12 arrangements and 6 teams or groups. Okay, now really, what was different over here? Hopefully we see that the difference was 12 divided by 2 equals 6, and that's how we got this answer over here, because every time we had AB, we also had BA. Those were different arrangements, but we're not going to count them twice. So really, we kind of doubled up the number of arrangements that we had for teams over here. So it was 12 divided by 2 equals 6. So for example 26, we have n distinct objects to determine the number of distinct groups. Now in the previous lesson, guys, we had something called number of distinct distinct permutations or number of arrangements, okay? So groups and arrangements or groups and permutations are actually different things. So this is what we call our combination formula. It's NCR equals n factorial over n minus r factorial, but we have an extra r factorial over here. Just want to go back for a second. So this over here, this number, was the same thing as 4 pick 2. And this number over here is the same thing as 2 factorial, okay? So the difference is, so the number of groups calculation over here, it came from the total number of arrangements divided by 2 factorial, divided by r factorial over here, okay? So over here, this part here was our NPR formula. So another way of writing the NCR is NPR over r factorial, okay? Or, let's rewrite this again. Okay, so how does this read? This reads as N choose R, okay? Which measures the number of groups of size R out of n possible. $27. In your pocket, you have a penny, nickel, dime, quarter, loonie, and a toonie. If you select 2 coins, how many different possible amounts of money could you select? Okay, so here's the idea for this. Suppose you select a nickel and a quarter. So idea over here, NQ, nickel quarter, is the same thing as QN, which is 30 cents over here, okay? So the point over here, if I take 2 coins in this situation and I'm measuring the amount of money I collected, it doesn't matter if I go NQ or QN, okay? So the first thing over here, if order does not matter, we are counting combinations. That's going to be groups. If order does matter, we are counting permutations. And permutations are arrangements. Okay, so this is a case where order does not matter. A nickel and then a quarter is the same thing as a quarter and a nickel. They're both 30 cents because we're talking about how many different possible amounts of money you could select. All right, well, each coin is worth a different amount, and we have 1, 2, 3, 4, 5, 6. This answer is going to be 6, choose 2. Okay, now let's put this down over here. NCR equals, so guys, I'm going to do this expansion the long way here. So in this case, it would be 6 factorial over 6 minus 2 factorial. 2 factorial is 6 factorial over 4 factorial. 2 factorial. Okay, now how do you expand something like this? We always expand the bigger term. So 6 factorial is the biggest number. So we go 6 times 5 times 4 factorial over 4 factorial 2 factorial. The 4 factorials cancel out. Now 2 factorial is just 2. 6 divided by 2 is 3. 3 times 5 is 15. Okay, guys, that's a long way of doing this calculation here. Quick ways is to use your calculator. And if I want to do 6, choose 2. You have 6, math, NCR 2. Answer is 15. Okay, so it gives us this calculation, which is really you guys doing the same thing as so it's doing the same thing as 6 factorial over 4 factorial times 2 factorial. So this is what this calculation is doing. And this answer is also going to be 15 over here. Okay, so this is what 6 choose 2 does, it does this calculation for us. Okay, so there's a little program in your calculator that when you enter this in, it does this math for you and gives the answer of 15. Okay, so back to our examples over here. The rest of this, guys, is like, the hard part is, like, I think one of the hardest parts of this unit is you need to kind of just read through a question and you need to decide, does the order of the selection matter? Okay, now to us, guys, group always implies order does not matter. Okay, but if order does matter, it becomes a permutation question. If order does not matter, it becomes a combination question. Okay, how many selections are possible? So, okay, there are 18 females and 14 males. The principal wished to make a group of 5 students. How many selections are possible if there are no restrictions? Okay, so 18 and 14, there are 32 possible people. There's no restrictions. So this question is going to be 32, choose 5. 32, NCR 32, choose 5 is 201,376. And we have that answer there. The group consists of 2 males and 3 females. Okay, so in this case, 2 males, well, we have 14 males. So 14 males, we're going to choose 2 of them. And then of the 18 males, we're going to choose 3 of them. Okay, 14 choose 2 times 18 choose 3. Is 74,256. Okay, the group is to consist of at least 3 females. Now, we need to be careful. What does at least 3 females mean? It could mean 3 females, and that would mean 2 males, or 4 females and 1 male, or 5 females and 0 males. Okay. A little trick to this unit, guys. The word and means multiply. The word or means we add. So here's what I mean by and or. If I have 3 females and 2 males, okay, and means multiply. 3 females and 2 males, we multiply here. Or means we add this case, 4 females and 1 male. Or 5 females and 14, choose 0. Now, first of all, guys, 14, choose 0 is just going to be 1. Okay, so it's always just this is going to end up being a 1. So I'll let you guys figure out what this is on your calculator, guys. But you're going to put in these three. So 18, choose 3 times 14, choose 2 plus 18, choose 4 times 14, choose 1 plus 18, choose 5 times 14, choose 0. And that's going to give your answer for this situation over here. Okay, so and means we multiply, or means we add. Okay, how many triangles can you make using the vertices of an octagon? Okay, so guys, you don't need to do in this level of detail every question, but what I'm going to do over here is I'm just going to label all the vertices of this octagon over here. Now, reason why I did this is, say I draw this triangle here and say triangle HFB. Okay, well, that is the same as triangle FBH. Okay, so the point I'm trying to make over here, the order of the vertices does not give a different triangle. Therefore, order does not matter. Okay, so this is why. So order does not matter for this question. So therefore, we're measuring combinations. We're measuring groups. Okay, so in this case, so here would be one triangle here, but this would be a different triangle. If I want GFD, that would be a different triangle, and if I want GHC, like that would be a different triangle, and so forth like that. So in this case, we have 8 vertices, and we need 3 of them in order to make a triangle. So this is going to be as simple as 8 choose 3. Okay, so I'm just going to go on my calculator for that one. 8 choose 3. 8 choose 3 is 56. There will be 56 different triangles in this question over here. Okay, a car dealer has 15 different mid-size cars. Okay, so part A over here, how many different ways can the dealer arrange 5 of them in his showroom? Okay, so the reason why I like putting this example here, arrange. Okay, well, arrangements implies that the order matters. Okay, so in this case, this would be a 15 pick 5 over here. Okay, so 15 pick 5. So when order matters, we use permutations. Okay. I'm going to do a little flow chart over here. So if order matters or if order doesn't matter, so if order matters, we could go to like a fundamental counting principle, which is like factorial notation, or we could use an NPR formula over here. Okay. So really, guys, I'm going to say these are interchangeable. The idea, guys, the NPR formula is supposed to be a shortcut for this guy over here for factorial notation or for fundamental counting principle. Another way of doing this with fundamental counting principle is when we have 1, 2, 3, 4, 5, and that means you have 15, then 14, 13, 12, and 11. But this calculation is the same thing as saying 15 pick 5 over here. If order does not matter, we have to go to the NCR formula over here. Okay, so it's just this is kind of the general decision we need to make for all of our questions. Consider the order. If it matters, we have to use one of these guys over here, and it gets different if there's repeated elements. We need to account for all that stuff over here. But if order does not matter, we just go to a combinations formula. How many ways can a rental agency purchase 8 of them? Okay, so this comes back similar to the coin question we just did. If there's 15 cars and I want to purchase 8 of them, okay, well, which 8 do I want? Well, if I chose, say the first 8, it doesn't matter which order I arrange those in, it's still going to cost the same amount. So this one over here, I'm going to say order doesn't matter. So we want to use our NCR formula. So this is going to be 15 choose 8. Okay. So guys, I'll let you guys enter these values into your calculator, guys. To me, the number like that, it's just that you guys can do over here. But you need to understand why we're doing each. Arrangement implies order matters. And in part B, this is a case where the order doesn't matter, because if I purchase 8 of them, it doesn't matter how I arrange those 8. The cost is still going to be the same. All right, example 31. How many different Lotto 649 tickets are there? If you buy one ticket, what's your probability of winning the lottery? Okay, so guys, here's a bit of practical math for you guys. So if you don't know, how does a Lotto 649 work? Okay, so if you look over here, the 6 is kind of bigger here. And what this means is 6 numbers, 1 to 49. Okay, so what it means is you need to decide which 6 numbers do you want to choose. Okay, and then you fill them in. This is essentially a Scantron. I know it's kind of blurry over here, guys, but this is like a Scantron sheet over here. So you label the numbers from 1 to 49, and you would select. You kind of fill in your 6 numbers over here. Now the idea over here, guys, the order does not matter. So suppose my 6 numbers were, say, 4, 12, 7, 28, 62, and then say 43. Okay, well, it doesn't matter how I arrange these numbers over here. I'm just going to fill them in on this bubble sheet over here. So the point is, guys, the order of your 6 numbers does not matter. Okay, now there's different lottery tickets like that. You may have heard Super 7 jackpot and stuff like that, and stuff like that. But so those are going to be you're choosing 7 numbers and so forth like this. So this question is, well, if I have from numbers 1 to 49 and I'm choosing 6 of them, my answer would be 49, choose 6. Okay. Now for the second part, what is your probability of winning the lottery? Guys, probability is really not one of our outcomes in this course, but we're going to do it for this question anyways. Probability of selecting a winning ticket equals 1 over 49, choose 6. Okay, so let's go take a look at what that answer would be here. 49, choose 6 is 13,983,816. I totally forgot what that was. 13,983,816. So therefore, your probability is 1 in 13,983,816. Okay. Here's a different question for you. If the jackpot is $2 million, is this worth it? And I'm going to say no. If the jackpot is $15 million, is this worth it? I'm going to say yes. Okay. because this is a case where we call something called expected value. Okay, so expected value is if you multiply the probability times your expected time to payout, so that'd be this times 15 million. If your number is over 1, that means you're expected to actually make money. Okay, I'm still saying, guys, you have a very low chance of still winning that over here, but it just we're talking about expected value. That's kind of how kind of like gambling games are kind of created like that, right? It's the expected value is going to be slightly in favor of the casino over the gambler. Okay, when I say slightly, it's not very much. Okay, but it is the reason why it's not very much, because if it was highly in favor of the casino and not in favor of the gambler, no one would play the game. But if there's a slight chance that the casinos, there's a slightly better chance the casino's going to win, okay, kind of gives a bit of a thrill there. You have a chance to win, so therefore you want to play the game. Okay, the idea is, after hundreds of people or thousands of people or tens or hundreds of thousands of people play the same game, over time, the casino is going to make slightly more on every single person on average, and they're going to make hundreds of millions of dollars in the long run doing this stuff. Okay, but it just the people still, because they like if I have a 48% chance of winning, I'm going to go bet money on that. Okay, like that. That's the kind of idea that the casinos are going to use to kind of get you hooked on these games. Okay, so guys, I'm saying again, just kind of the casino is kind of a good segue into into card games. Okay, so the diagram over here, in a deck of cards, if you've never played before, there are 52 cards. Okay, now the cards in a deck, you have an ace, a 2, a 3, 4, 5, 6, 7, 8, 9, 10. These are all number values. Okay, now an ace is 1. Sometimes an ace is worth high over here. Sometimes an ace is low. Don't worry about that. But we count an ace over here. So you have the kind of the numbered cards from here, and then you have face cards. You have a jack, a queen, and a king. Okay. Now over here, this symbol is clubs. This symbol is spades. This symbol is hearts, and this symbol is diamonds. Okay. Now the idea over here is that these are red cards and these are black cards. Okay. Now if you count them, you have ace to 10, there's 10 cards there, 11, 12, 13. So you have 13 clubs, 13 spades, 13 hearts, and you have 13 diamonds. Okay. You have 26 red cards, and you have 26 black cards. Sound good? Okay. Now, talk about assumptions we're making for these set of questions. When you say a 2-card hand, so if you have 2 cards in your hand, order does not matter. So if I had a 2 of clubs and an ace of spades, that would be the same thing as an ace of spades and a 2 of clubs. Okay, so the order does not matter like that. You can just kind of play those cards like that. It's not going to matter. Okay, so how many 2-card hands are possible? That would be 52. Choose 2. How many 2 cards containing only hearts is possible? Well, only hearts will be 13. So there's 13 hearts. If I want only hearts, there'd be 13, and I want 2 of them. How many 2-card hands containing 1 red and 1 black are possible? Okay, well, we have red and black. So if I want 1 red, that'll be 26, choose 1, times 26, choose 1. How many 2-card hands contain only face cards? Okay, so only face cards, well, there's 3 face cards here, 3 here, 3 here, 3 here. That means there are 12 face cards in the deck. Okay, how many 2-card hands are possible that have an ace and a face card? Okay, well, there are 4 aces. That'll be 4, choose 1, and you have 12 face cards. 12, choose 1. Okay, so the 12 face cards, you want 1 of them. Okay, guys, we're playing 21. That would be blackjack. Very good for you if you're playing that in the casino if you get that. Sound good? Okay, so this is how we kind of do these calculations over here. Guys, have you ever seen ever seen movies like there's a great scene in James Bond movie Casino Royale, okay, where the villain, his name is Le Chiffre, says, "Well, I have 2 pairs in my hand, and you have like an 8.5% chance of getting a flush," I think he says. Okay, so when he's saying that, he knows how many of this type of card, this kind of hand are possible, how many hands are possible, and he's actually kind of doing that probability calculation in his head. Okay, so when you hear about those stories about that, people who can go and just kind of quickly spit out probability odds when they're playing poker like that. This is essentially what they're doing. Okay, how many two card hands have only hearts? Well, there's 13 hearts. 13 choose 2. They're getting that number. Then how many 2 hard cans are possible? It was 52 choose 2. So the probability would be this number divided by this number over here, and they can do that very, very quickly in their head like that. Even those are people are very gifted at kind of dividing big numbers in their head and stuff like that, but they can figure that stuff out. Okay, more card questions over here. If you're dealt 5 cards, how many 5-card hands where all the cards are the same suit? Okay, so what this means is this would mean 5 hearts, or 5 diamonds, or 5 clubs, or 5 spades. Okay, so that would be 13 choose 5 plus 13 choose 5 plus 13 choose 5 plus 13 choose 5. Okay, could have gone 13 choose 5 times 4. It would have given the same answer over there. Okay, how many 5-card hands are possible that contain 3 hearts and 2 diamonds? Okay, so we know that there are 13 hearts in a deck. So we want 13 hearts, and we want to choose 3 of them, times there's 2 diamonds, 13 diamonds total, and we want 2 of them like this. Okay, so guys, I'm not finishing all these questions, but you would need to actually go and kind of put all these into your calculator to actually get a final number at the end over here for your final answers. Okay, how many 5-card hands are possible that contain at least 3 aces? Now what this means over here, this at least 3 aces would be 3 aces or 4 aces. Okay, now there's only 4 aces total, so there's no possibility of 5 aces because there's not enough aces. Okay, if it ever happens, guys, where you find 5 aces in a deck, that means someone's cheating and they're probably trying to hustle you out of some money. So what this situation is going to be would be 3 aces and 2 non-aces, or 4 aces and 1 non-ace. Okay, so 3 aces is 4 choose 3, 2 non-aces. Well, there's 48 cards that are not aces in a deck because there's 52 in total. So it's 48 choose 2, or means plus 4 choose 4. So out of the 4 aces, I want all 4 of them, times 48 choose 1. Okay, so this over here is going to give you the answer. So again, guys, make sure you do this in your calculator. 4 choose 3 times 48 choose 2 plus 4 choose 4 times 48 choose 1. Okay, example 34. How many pathways are there from point A to point B? Okay, I'm going to show you this question in 2 different ways. So when I say pathways, what we're implying here, guys, is that you could only be getting closer from this point to this point. In other words, I can't go backwards. And if you could go backwards and you could go up, you could just go in circles, and that means there would be infinite pathways. Okay, but we're saying so every time you move, you're moving either to the right or you're moving down. Okay, so here's what one pathway would be. So this would be right, right, down, 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 right, down, right, right, right. This would be one of these pathways over here. Okay. Here's another pathway. This would be down, 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 and then right, 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 right here. Okay, so this would be a different one over here. Now, guys, I mean, we couldn't do this all the way through. It would take way too long. But no matter how you do it, if I took so this is like my first pathway, this is my second pathway, I'm always going down 5 times, and I'm going to the right 6 times. So it comes down to how many ways can you arrange 5 Ds and 6 Rs. Okay, well, this becomes like a permutations question with repeated elements. Okay, well, this answer would be 11 factorial because there's 11 letters altogether, divided by 5 factorial, 6 factorial. Okay, so this calculation over here would get you this answer over here. Okay, so this is method 1. Okay, what I'm going to do over here, guys, I'm just going to erase this. I'm going to show you method 2. Method 2, as like I say, I'm going to do a pathways question like this. So if I'm starting here, how do I get to this corner over here? Well, there's only one way I can get to here. Okay, I can go to the right over here. Now to get to here, okay, and then to get to here, there's only one way as well, because I'm just going this way. So along the edges, it's going to be 1 like this. Same thing going down this way. So the only way I can get to this point is just going down like this. Okay. Now to this point, though, there's 2 ways, because I can either go through this point or through this point. And if there's one way to get to here and one way to get to here, there's a total of 2 to get to here. To get to here, there's 3 ways, okay? Because there's 2 ways to get to here and 1 way to get to here. 2 plus 1 is 3. This would be 4, this would be 5, this would be 6. This would be 3, this would be 6, this would be 10, this would be 15, this would be, no, 10 plus 5 is 15, 15 plus 6 is 21. There we go. 1 plus 3 is 4, 4 plus 6 is 10, 10 plus 10 is 20, 20 plus 15 is 35, 56. 1 plus 4 is 5, 21, 5 plus 10 is 15, 15 plus 20 is 35, 35 and 35 is 70, 126. We have 6, 21, 56, 126, 252. 1 plus 6 is 7, 28, 84, 210, 462 over here. Now, I'm just going to go on my calculator, guys, to figure out what this answer is over here. Ooh, look at that, same thing. Okay, so the point is, guys, we can do these questions either with kind of like a repeated letter permutation over here, or we can do it by, I'm kind of using it by point to point. Now, the reason why I showed you both methods, if you have a grid like this, guys, the best way to do it is with this type of calculation over here. Okay, I mean, much easier than doing this. Now, if you look at this one over here, hopefully you can see that, well, it's not quite the same because, like, you see this one, how like this right is not the same as going from here to here, because like there's 2 rights over here, but there's only 1 right over here. That kind of messes everything up. So for a question like this, we have to use the corner-to-corner method. So if I'm going from A to B, here's how this is going to look. I'm going to have ones on my outer edges, like this. Okay. Now for here, it's also going to be 1. Now let's do this one. 1 plus 1 is 2. 1 plus 2 is 2. This is going to stay 2 here. 1 plus 2 is 3. 1 plus 3 is 4. 3 plus 2 is 5. 5 plus 4 is 9. 5 plus 2 is 7. Let's keep working this way. So this is 1 over here as well. That means I have 1 plus 1 is 2. 1 plus 2 is 3. I have 2 plus 1 is 3. 1 plus 3 is 4. 3 plus 3 is 6. 6 plus 4 is 10. Now this is 6. This is still going to be 6 here. 10 plus 6 is 16. 6 and 2 is 8. 8 and 16 is 24. 8 plus 7 is 15. 24 and 15 is 39. 39 and 9 is 48. Okay, so this is how we do this question, going corner to corner from this guy over here. Okay, example 35. How many 5-letter arrangements are possible using 2 letters from count and 3 letters from hard? Okay, counting is hard, guys. That's why I kind of put this example in here. Now, guys, this is definitely the hardest question that we'll cover so far. And I think when I say the hardest question, guys, the calculation is going to be quite simple at the end when you see it, but just kind of understanding why. Now, the problem is, I don't know which letters from here I'm taking, and I don't know which letters from here I'm taking. So in this question, what we need to do first is select which letters from count and then select which letters from hard. Okay. All right. Here's how I have to do this question, guys. I'm going to show you the correct way first, which is probably going to be pretty confusing, and I'm going to show why this kind of works afterwards. When I'm selecting words from count, I want 2 letters from here. I have 5 letters altogether. I'm going to go 5 choose 2 times 4 choose 2. Now, hopefully, guys, you're saying, oh, wait a second, they're saying arrangement, so why aren't you using permutations? Okay, just bear with me for 1 second. My next step is going to multiply times 4 factorial. Okay, here's why I'm doing this. Okay, so this is going to be the correct calculation over here, and we'll get this answer in a second. Here's going to be the incorrect way to do it. So this is the correct way. Here's the incorrect way, which I think is probably the more intuitive way to do the question, but unfortunately, guys, it doesn't work out. The incorrect way is to go like this. 5 pick 2 times 4 pick 3. Okay. Now I see why. So well, the order matters. So I'm taking order from here. So order matters from count and then from hard. Now the problem with this is this would be one arrangement. So here these 2 letters came from count. These 3 letters came from hard. Okay, so C-O-A-R-D would be one possibility. Now the problem is, by doing this one first, I'm saying that the C and the O have to come first, but they don't. Okay, I mean, like, couldn't I have done like this type of arrangement? Okay, that could have worked as well. Okay, but the problem is, by saying 5 pick 2, I'm saying I'm picking these ones first and then arranging these ones second. But it didn't have to be in that order. What this is saying I'm selecting C, O, and then I'm taking, guys, my mistake. This is 4 choose 3, not 4 choose 2. Okay, so I'm taking 2 from here, I'm taking here, and then this 5 factorial, not 4 factorial, times 5 factorial would arrange all of these 5 over here. Okay, so this is the correct way to do this question, guys. You'll see a bunch of questions in your practice like this over here, guys. So hopefully you're coming across those ones as well, and that you'll be able to kind of follow this procedure for those type of questions. All right, guys. Guys, I know that this can seem a little bit overwhelming right now. Again, guys, this stuff just takes a lot of practice. Okay, so in your notebooklets and stuff, okay, I'm giving you guys a whole bunch of practice sheets on this stuff, guys, and you just need to keep doing these questions, and then to keep getting better at these ones altogether. Okay, all right, guys. I'll see you in the next video.